Let's discuss the topic of continuity. Continuity here implies that we're talking about the continuity of a function. We want to know if a function is continuously connected, or is there a certain point where the function is discontinuous? Meaning, is there a certain x value where the function is disconnected? So we'll gain much more understanding of continuity by looking at functions that are actually discontinuous at a certain number. Let's look at some examples. So for example 1, we're just going to draw the piecewise function here. And you'll notice my scale is actually not to scale. So I'm going to write that. I'm going to write NTS when I'm drawing things not to scale. Now the output is actually 4 when x is greater than or equal to 2. And the output is 3 if it's less than 2. And for this one, if you picture a stick person running from left to right, the only way you could get higher in the range values is by jumping and landing on that platform. So we actually call this a jump discontinuity. Now, for this function, f of x is continuous on two separate intervals. It's actually continuous on negative infinity up to 2. And it's continuous from 2 to infinity. But notice there's a bracket at 2. More importantly, we need to know that f of x is discontinuous at x equals 2. One way to realize that this is discontinuous is if you were drawing the function or drawing the function values from left to right, and if you ever have to lift your pencil or your pen up to draw the next function value, you know it's actually discontinuous at that point where you lift up your pencil. So I lift up my pencil at x equals 2, we know it's discontinuous there. Let's look at another example. Let's look at example 2. Example 2 looks like a straight line. However, x is not equal to 3. So that means 3 is not in the domain of the function for example 2. We could use slope y-intercept form. And you'll start to realize, because 3 is not in the domain, we have a removable discontinuity. So this is not called a jump discontinuity, this is called a removable discontinuity. Once again, the function is continuous on most of the x values, but not all. F of x is certainly discontinuous at x equals 3. Let's look at example 3. This time we have an upside down v shifted 2 units to the right and 2 units up. However, there's a hole there. And then when x equals 2, the output value is actually at 3. So this time this time 2 is in the domain and 3 is in the range, but there's still a removable discontinuity. Could you list the intervals in which the function is continuous? Why don't you give that a try? Make sure you state that f of x here is discontinuous at a very specific number, specifically at x equals 2. One last example. The last example here is a positive value function. It's shifted right 2 units using transformations from your algebra class. And whenever you're not sure, you're always welcome to make a t-chart. Pick as many ordered pairs as you need to get an illustration of the graph. Now we know there is a vertical asymptote at x equals 2. This is a positive value function. So notice when x equals 3, our output is actually going to be 1. And when x equals 1, our output will also be positive 1. And if you pick more values, you're going to realize this is a positive value function that behaves like this. And that's good enough to realize there is a discontinuity here. Once again, the function is mostly continuous, but however, it is discontinuous at a very specific x value. This time, this is not a removable discontinuity. This is not a jump discontinuity. This is actually an infinite discontinuity. You could say infinite discontinuity, or you could say asymptotic discontinuity. And so there are examples of discontinuous functions, where the functions are mostly continuous everywhere except at a very specific x value.